exist, but they are also continuous. In spite of that, these two turn out to be not equal. In fact, at one point we will see Clairaut's theorem, which will put conditions, further conditions in this situation that will ensure that these partial derivatives are equal. Okay, so but before that, it remains a mystery. They are not equal. Are they equal in some situations? In what situations? It seems like a mockery of or an insult to calculus, but it's really, we are making a fool of ourselves because we are not using calculus properly. That's why this this nonsense is coming out. Okay, then there is one more. Oh, yeah. Example 1 to 12. Lopitals Rule. This has been used successfully by many of us to find limits of functions, particularly when we have like indeterminate forms like 0 by 0, things like that. So, roughly the rule looks like this. We can differentiate both the numerator and denominator with respect to x, and we can replace them by their derivatives. F prime x denotes derivative. So f prime x is nothing but this. Okay. Now let's start our careless use of L'Hopital's rule. Let's look at this situation. This limit. Without even thinking what the limit is or whether the limit exists or not, we straight away start applying the rule. We differentiate the numerator with respect to x, we get 1. Differentiate the denominator with respect to x, also we get 1. So according to us, the limit has to be 1, which is of course wrong. Why? Because this limit is not 1. It's actually 0. Now someone may point out that this rule is applicable only when there is an additional condition. These limits are 0. This is 0, the limit of the numerator as well as the limit of the denominator. They are 0, which is not true for the denominator here. Here, if I calculate this limit, then it becomes 1. So maybe that's why we cannot apply the L'Hopital's rule here. Fine. So let's take another example. Okay, this function is there. For this one, I have to calculate the limit. I hope I have written it correctly. Yeah. Now here also we are blindly applying the L'Hopital's rule. So what we do, we differentiate the numerator and denominator separately with respect to x. Differentiating this will require the formula for differentiating the product of two functions. So we have 2x sine x to the power minus 4, then plus x square stays as such. Differentiating this with respect to x gives us minus 4x to the power minus 5 cos x to the power minus 4. Differentiating this one with respect to x gives us 1 in the denominator. So we have limit x tends to 0, 2x sine x to the power minus 4 minus 4 x to the power minus 3 cos x to the power minus 4. Okay, by the way, the condition that this numerator and denominator should both approach 0 when we take the limit, whether that is satisfied here or not, that we have not verified. So let's do that. Limit of the denominator, of course, is easy. It's 0. What about limit of the numerator? Without going into specifics, we just consider this. The sign value of something always lies between minus 1 and plus 1. This is a property of the sine function. Okay, so that means if I multiply both sides by x square, I can, because x square is non-negative. Then I have this. Now as x approaches 0, this approaches 0, this also approaches 0. So by the sandwich theorem, if you remember from calculus, this one approaches 0. So the condition that both the numerator and denominator should approach 0 when we take the limit are satisfied here. Minus 4 limit to the power minus 3, this. Now, just like we showed that this limit is 0, we can show that this limit is also equal to 0. However, if you look at this limit, there is a problem. Cos x to the power minus 4 is bounded, just like sine. Cosine also lies between minus 1 and plus 1. However, as x decreases towards, goes towards 0, 1 by x cube increases without any bound. So this limit does not exist. So from this application of Lopitals rule, we may be tempted to conclude that this limit does not exist at all. But instead of taking this extremely difficult path, if we just stop here itself and consider the fact that we can cancel x. Why? Because x is non-zero. Sine x to the power minus 4. Then this limit is 0 actually, because this is 0. So, not being able to use Lopitals rule or using it and getting an incorrect answer, something has gone wrong. What is it? Okay, so that also we have to answer at one point. And now the last example. The last example involves limits and lengths. You consider a right angle triangle which has both of its smaller sides equal to 1. Then according to Pythagoras theorem, this hypotenuse has length √2, square root of 2. Okay. Now instead of using Euclidean geometry, suppose we want to use calculus to find this length by approximation. What we do, we draw steps like this, like a staircase. We draw some steps. You see, this may not match, but that does not matter. What we do, we are considering n steps of equal length. What length? 1 by n. Or let me write it. N steps, or more specifically, n horizontal lines of length 1 by n each, and n vertical lines of, I'm running out of ink, just give me a minute. Okay, so n horizontal lines of length 1 by n each, and n vertical lines of length 1 by n each. So that means these horizontal lines, these steps, n number of them, and n vertical lines. Okay. Now, what will be the total length of all these lines? Length of one horizontal line is 1 by n, so namely n number of them will have length 1, or length this, plus vertical lines have, each one of them has length 1 by n. How many lines are there such? N. Here of course n has some value. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But we are increasing n. We are taking any number. So as we increase, these steps will be smaller in size, because the size is 1 by n. So as n increases, 1 by n decreases. So can you imagine that as we go on taking smaller and smaller steps, the steps, their total length will start to approximate the actual length of the hypotenuse. So this is the total length. So if we take this limit, it should give me the length of the hypotenuse. But what is this value? They cancel out. We have 2. So according to my calculus, the length should be 2, but it is actually root 2. So something has gone wrong. Again, my intuition seems to have failed. So it's a story of failures, and it shows how good we know calculus. It's because of these things that we need real analysis. And unless we know what we are doing and simply continue to blindly apply the rules of calculus, every now and then we will come across things like this. So with this is the motivation, and this is the reason we have to study real analysis. Plus there is a certain satisfaction in knowing why things work. So always approaching a problem engineering style, it will not work. Okay, plus if we uh, carefully learn analysis, it will help us tackle some things which are coming in future, which are more advanced. How we tackle those situations which are unfamiliar to us. Okay, so we will see that, and from the next video we will start analysis by starting to construct the system of natural numbers. Okay, so far we have assumed that we are given the system of natural numbers and we know many of its properties. Not here. Here we will actually construct this system, and gradually from this we will construct the integers, then rationals, then real. By the time we get to the real numbers, and in going from one system to a more complicated system which includes the previous system, when we make this jump from complex number to, from rational numbers to real numbers, we will see where analysis is coming from. Okay, and why these things are somewhat algebra, not much analysis. So there the actual mystery lies there in this jump. Okay, so with this I end this video. If you like what you see, please subscribe to my channel. And so I end this here and signing off from the mathematical room. Have a nice night.